Welcome to Year 11 Chemistry. Today we'll be discussing hydrocarbons and in particular alkanes. So before we start talking about alkanes in particular, we need to discuss what makes alkenes a family of molecules. So another word for that, or another term, is a homologous series. Molecules that contain the same functional groups react in very similar ways. That makes sense because the functional groups are the reactive sites on a molecule. So if a certain group of molecules all have the same functional group, then we would expect they have similar chemistries, so they react with other similar chemicals. So what differs within the same family basically is how long their carbon chain is. They all have the same functional group, but they have differing size molecules. So here we have three molecules shown. The first one being 3 carbons long with their carbon chain, and the second and the third having 4 carbons in their chains. So the difference between the top two and the bottom one is that the top two have a functional group that is the same, so functional group A, just being very generic right now, and the third one has a functional group B, so the third one has a different functional group. So we would say that the first two molecules belong to the same homologous series or the same family, whereas the third doesn't. It is separate. Because it has a different functional group, we expect it to have different chemistry. So alkanes are hydrocarbons. Basically, they lack a functional group. They lack a reactive site. So we draw it like this. So this is an example where we just have a linear carbon chain and each carbon is bonded to hydrogens. So the way we draw these molecules is we basically start with the 4 carbons, and then we have a single bond between all the carbons, and then we have to satisfy the bonding requirements for carbon. So you can see that carbon is group 4, so it needs 4 bonds to satisfy its octet shell, its valence shell, whereas hydrogen, being group 1 with a 1 single electron, only needs 1 bond to satisfy its shell. So that's why we have each carbon having each carbon having 4 bonds and each hydrogen only having 1. So each new member of the alkane family is created just by adding a new CH2 group within the molecule. So that's how we generate the general formula. So basically the general formula starts with what we call methane, so it would just be a single carbon molecule. If you can imagine just a hydrogen there, you'd have a single carbon. And then each time we add another carbon to the chain, we just add 2 hydrogens to the formula. So the general formula just allows us to quickly calculate a chemical formula for an alkane. So now we are discussing the naming process of these molecules. So it's very good with our homologous series. They all have the same ending to their name. Just like our family names, we all belong to the same family, so our last or surname or family name is always going to be the same. So the alkanes, all the molecules have ane on the end of their name. And the beginning of the word, or the prefix, is determined by the carbon chain length. So here we have a list from 1 to 10, the prefix or the beginning of the word, depending on the number of carbons that we have. So this is a good resource to copy down, and then we'll use it to do some problems. Okay, so now we're going to start naming alkane molecules. So I'll talk through the first one. So we have 3 carbons in our molecule. So we are looking at using the prefix prop because we have 3 carbons. So we just then join the prefix prop with ane, because we are dealing with the alkane family, so we have propane as a result. So have a go at trying to name this molecule here. So first count the carbons, determine the prefix, and then join on the family suffix. Okay, so we can see that we have 1, 2, 3, 4, 5, 6 carbons in our chain. So we're looking at using the prefix hex. So we've just used hex and then joined on ane on the end because we are looking at the alkane family. Okay, so now we are given the name of a molecule. So use our knowledge from before to draw these two molecules. So pause the video now and have a go. Okay, so if we're looking at butane, we're looking at the alkane family once again, and we're looking at having 4 carbons in our chain. So we're going to draw 4 single bonded carbons together, and then we're just going to draw 4 bonds around each carbon to satisfy the carbon's octet shell. So we get the structure shown here. With heptane, we have 7 carbons in a linear line, each with a single bond, and following the same steps, we just make sure each carbon has 4 bonds. So we just satisfy it by filling in with hydrogen. So now we're going to discuss the alkane's physical properties. So when we're talking about physical properties, we're discussing solubility, melting point, and boiling point. So first we'll talk about solubility. So solubility is all about the polarity of the alkanes. So with polarity, what we are talking about is whether the molecule has a partial or full charge on the molecule. So this comes about from large differences in electronegativity. So basically, electronegativity means, the higher the electronegativity, it means the atom wants more of the electrons within a bond. So if we have a partial charge on a molecule, so we're going to have a positive and a negative end, and then those molecules can electrostatically attract one another. And molecules with a similar polarity, they are basically, because they have, either they'll have a polarity, so they'll be polar, they'll have charged ends, so they'll electrostatically attract, so they want to stick to one another, so therefore they'll be soluble in another polar substance. Whereas if it's a non-polar substance, it basically, because they lack that polarity, that charge, they all have similar interactions, so they'll also only be soluble within one another. So here we have it. So here's a table showing the electronegativities of hydrogen, carbon, and oxygen. So we're just going to compare a generic alkane. So this alkane is a butane, and we're going to compare it to water. So we can see that carbon and hydrogen aren't very electronegative. They are very similar, both around 2.5. That's not a large difference. And we also notice that our molecule is highly symmetric. So it's symmetric down the middle here and the middle here as well. So it's highly symmetric, and it has low electronegativity difference within its bonds for each carbon-hydrogen bond. So we would expect the carbon molecule to be nonpolar. Whereas water, we have a large electronegative difference between the carbon and the oxygen. So each bond within water has a large electronegative difference, oxygen being the more electronegative. So each electron within these bonds is going to spend more time around the oxygen atom. So this end of the molecule will be slightly negative. It's only slightly partially negative because the electrons aren't permanently fixed on the oxygen. They just spend more time there. And the hydrogens are slightly positive, same reason. So we'd say that the butane is nonpolar, or the generic alkane is nonpolar, whereas water is polar. So when these two molecules are mixed, basically because the polar molecules have that charged end, the positive end of another water molecule is going to interact strongly with that negative end. That positive and negative attraction, electrostatic attraction, is the reason for that. Whereas the alkane just won't interact strongly with this water molecule. So they tend to separate into layers when they are mixed. So here's just a diagram showing a aqueous or water component mixed with a alkane, and they are just coloured so we can see the difference between the two. Now, the next physical property is the melting and boiling points of the alkanes, and these are all determined by the strength of the intermolecular interactions. So with our alkanes, because they lack dipoles, so a permanent large electronegative difference within the molecule, so with the carbon and hydrogen from before, we saw that. They also lack an ion or a charge component, permanent charge component, so they can only interact using weak London dispersion forces. So here we have a diagram describing this. So normally these molecules would have no charged ends, but when they are stacked nice and close to one another, they have this interaction where the electrons on one side of a molecule are pushed to the other side. So we have our electrons on this molecule being pushed to the left-hand side, and our nucleus, being a fixed positive charge, stays in place. So overall we have a negative charge on one side of our molecule and a positive charge on the other. Then, because we have a positive charge on this, or slightly positive charge on this side of the molecule, this side of the middle molecule will have a larger distribution of electrons. So they have a slight electrostatic attraction. But the reason why it's weak is, one, it's only temporary. These are instantaneous, only happening in picoseconds, very small time scale. So they all of a sudden quickly attract one another, and then all of a sudden the distribution of electrons goes back to normal. So it's very on, off, on, off, on, off. So they have a weak London dispersion interaction. So that's why they interact weakly, and they easily boil off or melt. So alkanes typically have a low melting and boiling point. So alkanes are classed because they have a lack of a reactive functional group. So it's not surprising that alkanes are known only for their complete combustion reactions. So these are very similar to our reactions that are found in our internal combustion engines. So the word combustion is a very good reason why they use it, because the alkanes and other similar chemicals go through a combustion reaction in our engines to give out energy for our cars, but they're also notorious for their production of carbon dioxide. So they've got a lot of bad press for that with our fossil fuels. But in terms for us, what happens is we have our carbon species will change each time we approach these questions, but we will see that our oxygen, carbon dioxide and water is always permanent within these reactions. The only thing that change is the coefficients out the front of those species. So first we count up how many carbons we have in our molecule. We have 3. So we have 3 in front of the carbon dioxide. We then balance by putting 4 in front of the water. And then we count up our total oxygen atoms we have on the right hand side. We have 3 times 2, so that's 6. Plus 4 lots of water, oxygen. So we have overall 5 lots of 2 oxygens on the right hand side. So it's often easiest to balance for oxygen last with these equations. So have a go at writing the complete combustion of pentane and octane. You may need to go back and have a look at the prefix list that we saw before, and also with the family general formula for alkanes, and determine the chemical formula first so we can do the complete combustion reaction. So pause the video and have a go at writing the complete combustion reaction for these two molecules. Okay, so we see that we have pentane having 5 carbons, and because it belongs to the alkane family, 5 times 2 plus 2 gives us the number of hydrogens in our formula. Balance for carbon with 5 at the front, and then for hydrogen with 6 for the coefficient of water. We count up the total oxygen molecules. We have 10 and 6, so 16 divided by 2 it gives us 8 oxygens. Now with octane, interestingly, we balance by having 8 and 9 out the front of our carbon dioxide and water, but when we count up our number of oxygens, we achieve 25 oxygens on our right hand side. But we just write it as a fraction in front of the oxygen. That is perfectly fine. It is not saying we have half an oxygen atom. Basically, they're just reacting in a ratio. A bit like when we bake a cake, it's perfectly fine to use, for example, 5 tablespoons of sugar and 1.5 litres of milk, for example. Just because we're using a particular ratio of these molecules doesn't mean we actually change the structure of these molecules. So that's perfectly fine to have a fraction as a coefficient. So that reaches the end of our video. So thanks for listening. So next video we'll be talking about alkenes and their similar physical and chemical properties.